Hello, welcome to StudySync. This video brings us to the principle of mathematical induction. So in this video, we are going to look at the principle of mathematical induction, and we'll take some examples and look at how it is used to prove certain identity and equation in mathematics. Now, the principle of mathematical induction is important. It's a very important property on the positive integers, so on the set of positive integers only. So integer z, so positive ones. So this is the set on which the principle of mathematical induction applies. Now, what does this thing all help us to do? So it helps us in proving statements involving these positive integers, especially when it is known for some numbers in this set. So for example, let's say an identity or a statement is known for z equals 1 and 2, and it is presumed that it could be true for all other integers. Then the principle of mathematical induction is what helps us to establish this statement as either true or it is false. Now, what this is going to mean is that first we are going to prove the statement. So let's say we have a mathematical statement P that we assume that, or let's say we can verify that it is true for some integers, say 1 and 2, but then we presume or assume that it is then going to be true for all other integers to infinity. Then what is we are going to do first in proving it is that we are going to verify the statement P for n equals 1. Possibly 1 could be the least, but we know 1 is not the least integer. It could be 0. So some of these statements come with their ranges, where they define their ranges. So we'll look at some of them in the examples we'll solve. So the first thing is we are going to establish or verify the statement to be true for n equals 1. If that is verified, then the next thing we are going to do is that we are going to then solve this implication. So we are going to say if, so the implication, so P K implies PK plus 1. So we are going to verify that this is true. So now when we verify that this implication is true, so when true, then this is where we establish that the statement P, then P is true for all n being what? A positive integer. So from 0 going to infinity. So these are the simple steps that we are going to be doing in mathematical induction. So prove it, and then so let's take one quick example. So the first example we are going to look at over here is to prove that, so prove that 1 plus 2 plus n is equal to n multiplying n plus 1 all over 2. So we are to prove that this statement, so the statement here P is 1 plus 2 plus on up to a particular n, which is an integer, equals n multiplying n plus 1 over 2. Now what we are going to do first is that let's verify it for n equals 1. So that's the first step we are going to do. So let's verify it for n equals 1. Now let's check. So if n equals 1, then what we are going to get at this part of the equation is just what? 1 equals, now let's substitute n equals 1 into this part of the equation, then we get 1 into 1 plus 1 over 2, which is equal to 1 multiplying 2 over 2, which is 1. The 2 cancel out. So hence we've established that 1 equals 1 from the particular statement. Hence we are able to verify the step 1. Now the next thing we are going to do is that let's check if the implication P of K implies P of K plus 1 is also true. So this is the next thing we are going to do, and this is where the main work is. So once you are able to verify this, then the statement is true for all other integers which are positive. So positive integers. Okay, now the next thing we are going to do is that let's say the statement, so P of K, so it means 1 plus 2 plus K should be equal to K into K plus 1 over 2. Now this is the left side of the implication, which is this one. Now we are going to verify if this implies P of K plus 1. So this is P of K. Now P of K plus 1 will give us 1 plus 2 plus on plus K. Then what are we coming to do? We are now coming to add. So let's add K plus 1 to the equation. So K plus 1 is the last element. Now what that is going to mean is that, so let's try to prove this. So we are coming to now expand this to now come and get this. If we are able to arrive at an expression that is similar to this, then our implication is true. Now when we look at this series from 1 all the way to K, it has been defined by this particular expression we have over here, which is K multiplying K plus 1 over 2. So it means we can rewrite this to look like K into K plus 1 over 2, then plus K plus 1. So 1 plus all the way to K over here is what we have over here. Then the last addition, which is K plus 1, is what we have over here. So now let's work on this particular term. So let's write this in the next page. So K into K plus 1 over 2 plus K plus 1. Now let's try and perform some simple arithmetic over here. When we expand this, we'll have K into K plus 1 over 2. We can make this all have the same denominator by multiplying this term by 2 and dividing it by 2. So 2 into K plus 1 over 2. So now let's expand everything. So this part you can expand it and we get K squared plus K, then plus 2K plus 2 all over 2. Now let's try to simplify the numerator to give us K squared plus 3K plus 2 all over 2. Now the numerator is factorable, which is K squared plus 3K plus 2. When we factorize that, we are going to get K plus 1 multiplying K plus 2 over 2. Now we are almost done, but our goal is that we want to establish this part. So we want to make sure that this PK implies PK plus 1. So it means that we want to write that our final equation that we have. So we want to make sure that this equation we have looks in the form K into K plus 1 all over 2. So it's just like a number multiplying the number plus 1 over 2. We are trying to achieve the same thing over here. Just that here what we are working it is now, let me clean the implication. Here what we are working is now P of K plus 1. So what we are working is K plus 1. What we did initially was K. So if we are working now with K plus 1, it means we should be able to have the number we are dealing here is now K plus 1. So the question is, can K plus 1 multiplying K plus 2 be written in this form? Here the number we're dealing with was K, where K is K, the number K multiplying the number K again plus 1, then divided by 2. We want to achieve the same thing over here, and it's very achievable. So here it means K plus 1. We can expand the K plus 2 to look K plus 1, then plus 1 is the same as K plus 2, then over 2. Now we can see that it's also looking like this. as before. So k plus 1 is the number we are dealing with at the right side of the implication. So k plus 1 is the number. Now multiplying that same number plus 1 over 2. So hence our implication is true. So this implication is true. So once we're able to verify this implication, it means that 1 plus 2 plus n equals n into n plus 1 over 2 is true for all n belonging to what? The positive. So a set where the members are at positive integers. Okay, so now let's take another example. So we are to prove that for all n greater than or equal to 3, for all n greater than or equal to 3, 2 to the power n is greater than n plus 4. So this is what we have to prove. So as the method implies, so let's try and verify it for n equals. So here our set is starting from 3. So we can't use 1 obviously because 1 is not part of this ring. So we have to verify for n equals 3, which is the first element. If it is true, then we continue with the implication. So now let's check for n equals 3. N equals 3, it means we are going to have 2 to the power 3 greater than 3 plus 4. And this implies 8 is greater than 7, and that is true. Okay, so this is true. Now let's move to the implication. So for k, so let's do implying k plus 1. So k, it means 2 to the power what? K should be greater than what? K plus 4. This is the first thing we have. Now let's work on this. So now this is the first statement. Now let's try to verify it for 2 to the power k plus 1 should also be greater than what? K plus 1 plus 4. Now this is what we are coming to work with. Now let's check this side. So 2 to the power k plus 1 is equal to 2 to the power 1 multiplying 2 to the power k. Now let's do some kind of manipulation over here. Now 2 to the power k, as we saw from the previous statement, so from this inequality, this 2 to the power k, we realize that it is greater than k plus 4. So now if 2 to the power k is greater than k plus 4, then we should also expect that 2 multiplying 2 to the power k should be greater than 2 multiplying that k plus 4. This should make sense. We saw that 2 to the power k was greater than k plus 4. Hence, when we multiply 2 to the power k by 2, then we should expect that it should also be greater than 2 multiplying the k plus 4. So now, expanding this side, so 2 multiplying 2 to the power k is greater than 8. Maybe put the 2k first. So 2k plus 8. Now, originally, this is what we are trying to verify, that 2 to the power k plus 1, where is it, is greater than this k plus 1 plus 4. So 2 to the power k plus 1 is greater than, let's simplify this one, which is k plus 5. Now, we're able to work through and see that 2 to the power k plus 1, which is this term over here, which is the same as 2 multiplying 2 to the power k. We're able to verify that 2 to the power k plus 1 is greater than 2k plus 8. This is what we've come to arrive at. But what we are trying to prove is that 2 to the power k plus 1 is greater than k plus 5. Now, obviously, if k is an integer greater than 3, so it's a positive integer, then that should mean that 2 to the power k plus 8 should be greater than what? K plus 5. provided k, and we've already seen it from the question that the k here is a positive integer greater than 3, then that should make sense that 2 multiplying k plus 8 should be greater than k plus 5 for any integer k greater than 3. This statement should be true. Now, if you realize from the transitivity axiom, where we say that if A is greater than B and B is greater than C, then A is greater than C. So you can use this transitivity axiom to complete your proof over here. Now let's apply it. Now we've proven that 2 to the power k, this is what we're doing, 2 to the power k greater than k plus 4. Now we're trying to prove it for 2 to the power k plus 1 greater than k plus 1 plus 4, which is 2 to the power k plus 1 greater than k plus 5. But then we've realized that 2 to the power k plus 1, we've gone through the proof and we saw it was greater than what? 2k plus 8. And 2 to the power k plus 8 is greater than what? K plus 5, because k is a positive integer greater than 3. Now, we've able to verify that this is true based on our proof, and also we've seen clearly that this is also true. So now this is greater than this. So let's take this as our A, this is our B, this is the same B, this is C. Now realize that A is greater than B and B is greater than C. Hence, A also is greater than C. Now A, which is 2 to the power k plus 1, greater than C, which is k plus 5, is what we were trying to find out for. And this is true based on the principle, or sorry, the axiom of transitivity. Hence, our proof is correct. So it follows then that 2 to the power n is greater than what? N plus 4 for all n greater than or equal to 3. Okay, now let's look at one very last example. So let's look at 3 divide. So let's prove that. So the very last example we'll look at is 3 divides 2 to the power 2n. Write this well. 2 to the power 2n minus 1 for all n natural numbers. So natural numbers are basically positive integers. So for all natural numbers, 3 is able to divide 2 to the power 2n minus 1. Now, if they say 3 divides a particular number, so let's look at this before we come back to the question. If we say 3 is able to divide a particular number, let's use something C, it means that C over 3 is giving us what? An integer. An integer or a whole number. So that's what it means if we say 3 divides a particular number. So let's call this integer, let's say I. So that's trying to tell us C is equal to what? 3i. So the I is an integer, the C is also an integer, and obviously 3 is an integer. So it means that we can represent this whole expression over here. So 3 is able to divide this whole expression, which evaluates a particular number C as 3i. So we can say that what? 2 to the power 2n minus 1 is equal to 3i. So now let's verify for n equals 1. That's the very first step we do. So let's verify n equals 1, or better still, we can even start with 0. So for n equals 0, we'll do for both of them. So we'll do for n equals 0 and n equals 1. That's what the principle started with. That we know that it is true for some few values of n, which is starting 0, 1, and 2, obviously. But we want to presume first that it is true for all integers. Then the next thing after verifying this is that we'll go to the implication and do the verification. So let's see 2 to the power 2n minus 1 for n equals 0. We'll get 2 to the power 2 into 0 minus 1, which is 1 minus 1 equals 0. And of course 0 over 3 is 0. 0 is an integer. 0 here is an integer. So 3 divides 0. Now let's do for n equals 1. That's we get 2 to the power 2 into 1 minus 1, which is 2 to the power 2 minus 1, which is 3 as a result. And of course 3 divides 3 and gives us 1. So the next thing, now we verify for at least two of them, which is n equals 0 and n equals 1. Okay, now let's do the implication. P k into 2 implies p of k plus 1. So now let's verify if this implication is true. So once you're able to verify that this implication is true, then it means that the statement given in question is true for all integers in the range. Okay, so 2 to the power 2n, so k, so this k we are using now k. So now let's expand for 2 to the power k plus 1. Sorry. Minus 1. So now when we expand this, we get 2 to the power 2k plus 2 minus 1, which is 2 to the power 2 to the power k. Sorry. Two to the power 2k multiplying 2 to the power 2, then minus 1. Now we can expand this 2 to the power 2 to give us 4. So 4 multiplying 2 to the power k minus 1 is what we have now. Now over here, let's do a manipulation. Now the original statement we have on the left side of the implication is 2 to the power 2k minus 1. And we've established that this 2 to the power 2k minus 1 is a number which is divisible by 3. And we've represented this by 3i. So it means let's manipulate this expression to bring out this. We can do that. And when we look at this, we can rewrite minus 1 as minus 4 plus 3. So when we have minus 4 plus 3, then it's going to give us the same negative 1. So let's rewrite this as 2 to the power k minus 4 plus 3. Now let's factorize out the 4. It's because we want to get this form in this particular expression. That's why we are using 4, because 4 is multiplying the 2 to the power k. It's multiplying 2 to the power k, so we have to bring 4 so that we can factorize out 4 easily. So in the factorization, we have 4 multiplying 2 to the power k minus 1 plus 3. Now this 2 to the power k minus 1, 2 to the power 2k. This 2 to the power 2k minus 1 is 3i. Now let's replace that with the 3i. So 4 multiplying 3i plus 3 gives us 12i plus 3. Now this expression, we can factorize out 3. And when we factorize out 3, this expression is going to look 3 into 4i plus 1. Now I is an integer, so we are not likely going to get a fraction after we do this expression. When we substitute any integer over here, as we defined earlier, we are not going to get a fraction. So 4i plus 1 is definitely going to give us another integer. From the axioms or properties we learned, 4 is an integer, I is an integer. So 4 times another integer should give us an integer, which is the closure property. And that integer plus another integer is still closure under addition. So we are going to get another integer. So since we have an integer over here and it's multiplying 3, then obviously it means an expression like 3 multiplying another integer where it is now 4i plus 3. It means this expression should effortlessly be divided by 3. And that's going to give us what? 4i plus 3. So this is a final expression we've arrived at, which is 3 into 4i plus 3. And we can see clearly that this expression is divisible by 3, and hence our implication is true. So we're able to establish that p of k implying p k plus 1 is true, and hence 2 to the power 2n minus 1 is true for all n, which is a natural number. Thank you. Don't forget to like this video and subscribe to the channel and share as well. See you in the next lesson.